So let's wrap up and summarize some of the things that we've learned. We've learned about parallel communication patterns, going beyond the simple map operation that you saw in Unit 1 to encompass other important communication patterns like gather, scatter, stencil, and transpose. We've learned more about the GPU programming model and the underlying hardware, such as how thread blocks run on streaming multiprocessors, or SMs, and what assumptions you can make about ordering, and how threads and thread blocks can synchronize to safely share data and memory. We've learned about that GPU memory model, topics like local and global and shared memory, and how atomic operations can simplify memory writes by concurrent threads. Finally, we got a quick preview of strategies for efficient GPU programming. The first principle is to minimize the time spent on memory accesses by doing things like coalescing global memory access. We saw that the extremely fast global memory on the GPU operates best when adjacent threads access contiguous chunks of global memory, and this is called a coalesced memory access. We also learned to move frequently accessed data to faster memory, so for example, promoting data to shared memory. And we learned that atomic memory operations have a cost, but they're great and they're useful, and you shouldn't necessarily freak out about the cost. Often the cost is negligible, but it's something to be aware of. Along the same lines, we learned about avoiding thread divergence that comes with branches and loops. And once again, thread divergence comes at a cost. You should be aware of that, but it isn't necessarily something that you should be freaked out about. We're going to revisit these topics and talk much more about optimizing GPU programs in Unit 5. So that's it.